Defina. Can you hear me fine? All right. Can you hear me fine? Can you hear me fine? Yeah. You have to stand.
Yeah, please sit down. Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. I hereby formally open the session and welcome you all to the public defense of Nicolas Emborg-Jannsen. Nicolas Emborg-Jannsen has presented to the faculty his thesis on the topic mock simulations for ESA's Plato mission exploration of supermassive stellar objects with the next space-based photometric legacy. And this in partial fulfillment of the requirements for obtaining the degree of PhD in Science, Astronomy and Astrophysics. Nicolas Emborg-Jannsen shall now publicly defend the PhD thesis. Nicolas Emborg-Jannsen, you're invited to give a presentation of about 45 minutes about your work, and afterwards the examination committee will ask questions and discuss the work with you. I give now the floor to Nicolas Emborg-Jannsen.
Thank you so much. Thank you everyone for being here today for my public defense on the topic of mock simulations for ESA's Plato space mission, exploration of massive, supermassive stellar objects with the next space-based photometric legacy. And so this is a quite big title. I want to break it down to you over the course of this presentations as we usually do. So what I want to do in the beginning here is to give you the understanding of why we first need Plato in the first place. So the Plato mission is going to be launched in around 2 years from now, in December next year. And the reason for this is because if we look in a diagram like this, where we are looking at all the detected and confirmed exoplanets we have to date, we have around 6,000 of those. And we can also measure some of the parameters of these planets. So that could be, for example, the mass, as you see here on the y-axis, or the orbital period, as you see on the x-axis here. And the way we detect these planets is, for example, with different techniques. The one I will focus on in this talk is the transit technique, which is essentially something you're very familiar with. It's the case where you see, for example, a solar or lunar eclipse. So in this case, we have just a planet transiting in front of its host star. And what you see is this characteristic dip in the intensity over time of the star. And this is sort of the fingerprint when we want to go and discover and find exoplanets. So now we've returned back to this diagram of all the planets we have sort of found and confirmed to date. We can see that, well, if you look at this planets that are very similar to the more gaseous ones and the bigger ones in our solar system, just like Jupiter, Saturn, we have quite a few of them. But we don't have a lot of planets that are in the regime of our own Earth and even smaller rocket planets. And so this is what we are lacking in our observations, and this comes from observational biases of these space missions or ground-based telescopes that are looking for these planets here. So Plato is trying to fill out this space in this mass period diagram, and hopefully it will find another Earth-like planet on top of also characterizing a lot of new terrestrial planets that we're going to find out there. So let's look at the title again here, ESA's Plato Space Mission, the next photometric legacy. So what does it actually mean? What does Plato do? And what kind of data products are we going to get out of this? So if you look at the Plato spacecraft as a whole, it's a bit more complicated compared to its predecessors. So, for example, instead of having just a single mirror telescope, we now have actually 26 cameras. And you can see here in the top, 2 of those are what we call fast cameras. They are for the stability of the spacecraft. Then we have 4 groups of 6 cameras each, so amounting to 24 cameras. And here, these cameras here can be used in combination, depending a little bit on how they are looking into the sky. And so these cameras are split up in 4 groups because they don't point exactly the same space, in the same direction in space. And if we look towards the sky and what they actually will be covering, we make this beautiful visibility flower, as I like to call it, where you can see that if you have a star in the center here of a field of view, it will be observed with all 24 cameras. But as you move outwards, then we actually are having a bit more noise because we have less cameras, for example, 18, 12, and 6 cameras. Plato will be, as I said, launched in a bit less than 2 years from now. It has a commission phase of half a year, and then it has 4 years a mission duration after that. And what is planned so far is that Plato will first look here in if we take the projection of the entire night sky onto a galactic coordinate system, and we put the galaxy, our own Milky Way, here in the middle, we can see that Plato will observe 2 fields of a duration of 2 years each. The first one is already decided. That's the southern field here, which actually overlaps with the large Magellanic Cloud, which is our nearest dwarf galaxy. And the other one at the top here overlap with another space mission, which has been very important for exoplanets discoveries, namely the Kepler mission, which I also will talk a little bit about a bit later here. But what are Plato actually giving us? What is the data products we're going to get out of this? Well, Plato is a photometric mission, so that means that it's taking images, as you see here, a lot of them. But since Plato is limited also about the amount of data that can be stored on board the spacecraft, it's sometimes a bit easier to lower the telemetry budget. That's the amount of data we have to send to ground. And we take small images around each of the stars that we're interested in, and we download those to ground. So in the mission here, they're called imagettes, and they are 6x6 pixel images. And pixel images are simply just the same as you know from your own phone, a big pixelated data here with the star in the center, and there might be other stars as well, contaminating this main target. The method of photometry is essentially very simple, because we just now take this stack of images here, and for each of them, we now have to measure how much light is there in each of the frames. And we have 2 main techniques to do that. We have what is called aperture photometry. We simply just take each of the pixels, and we count up how much light do we find in this aperture. Or we can do it a bit more fancy, and we can use the instrumental profile of a star seen through the instrument, and we call that typically a point spread function. But I'm going to focus on specifically on the aperture photometry technique in the top here, because that's what I've been using throughout my PhD. The mission will provide both, and the mission will also provide both these imagettes that we can download to ground, and the light curves that will be processed on board the spacecraft. So now what you see here is simply just what we call a light curve. It's the measurements we take for each single image, and we put a data point on a figure here as a flux or intensity over time. And so those are very important because that's essentially what I've been doing for 4 years, looking at these things. All right, so I talked about the main core science of the Plato mission, but obviously many missions like Plato, they can also be used for a lot of other stuff. In this case, we were looking at exoplanets, the discovery of exoplanets, and also their host stars, which are typically like our own sun. But in this case, what we're interested in is looking at all the science we can do outside this little niche box. And we actually have around 8% again, the telemetry, the amount of data we can download to ground, and we can apply for these things through what is called a guest observer program. And so the complementary science program here, as the big title, is essentially gathering all the scientists to work on what we can do with a space mission like Plato if we were giving 8% of the telemetry. We have done this by putting everything into groups, into what we call work packages. And each of the work packages has sort of a lead that takes care of some of these scientific disciplines getting shined a light upon, and then we can see if we can maybe do something with Plato for these things. And I have been lucky to work on this actually in 2 different work packages, so that's what I'm going to focus on for the rest of the talk, including the simulations, of course. But one of them is the work package on pulsating stars, which we really want to highlight here. And another one is on transient phenomena, well, actually more extragalactic science and astronomy. But I will come back to these 2 things later. So my main goal of my PhD has basically looking into this complementary science program, and we want to exploit it as much as possible. Of course, it's only limited to 4 years, so I didn't have time to do all of the work packages, but maybe in the future that will be possible. But in another sense, from my point of view, what I've been doing is also a bit technical because I've been producing simulations, which I will come to in a bit. So we are really looking into the capabilities of this mission as a whole. So what can we do with this instrument? And the scientific discipline, I just said, that's the exploitation. And then also, obviously, the main goal of all of this is, in the end, we want to be successful when we make proposals in the future with the guest observer proposals. So with simulations, that's our aid and a tool to prove that we can do a concept, right? So that's what we're doing here. So for the rest of my talk, the outline here is simple 3 steps. I'm going to give you an introduction to the main software tool, PlatoSim. Then I'm going to show you our biggest study on astroseismic catalog, MOCA. And I will look into the very faint regime of hunting for supermassive black hole binaries, actually, with Plato, if that's possible. And we will finish off then. So let's look into now the title here at the top, simulations, or mock simulations for ESA's Plato Space mission. So first of all, before we go into which type of simulations that I actually do, why do we need simulations in the first place? And you might be wondering just like, why don't we just wait for the spacecraft to be launched so we can take the data when it comes to time? Well, there's a lot of things we need to test before a mission can be successful. And so for Plato, for example, that's a journey of maybe up to 15 years before the launch. And so we do everything from the preparation, commissioning, and operation of the space mission. There, a simulator can be a very, very valuable tool to help you assess if something is good or bad, or which direction we should go in. There's also the point that, well, compared to going to La Palma and kind of repair your instruments, we are going to send our telescope into the second Lagrange point here, which is basically this metastable point that are equaled out by the gravity of the Earth and the Sun. And so we were never going to see it again, so we better make sure that everything is correct. So we use this simulation tool, which have a long history and heritage here at KU Leuven, and I'm very happy to be a part of this collaboration and developing on it as well, and expanding its use cases. And the simulator that we are using here, PlatoSim, is of course designed for the mission specifically. So it simulates one of these cameras here, as you see, that we also saw was mounted on the optical bench of the spacecraft. And we simulate everything from the photons that come in from the sky, or stars, all the way through the optics here, and then onto the focal plane array, where we have a few detectors that can then read out all of the data. So that's a lot of different kind of physical processes that need to be modeled in this process as well. So what you get out of it is obviously images, if you use a pixel-based simulator. And if you then will take a simulation like this, where we just have placed a little subfield, again, we come back to the same main data products, which are the imagettes that I already mentioned. And those one consist of here for a prime target of a star in the center, which is our target that we are interested in. But we also have these stars that are contaminating our prime target, which is quite important for this kind of simulations that we're looking at later on in this species. PlatoSim models not only these simple images by looking at photons that comes in, but we actually also model every kind of thermal environment and movements of the spacecraft also doing so. So we actually take into account the stability, you see, of the instrument. So the little jitter you see there is actually because of the spacecraft itself is not completely stable. We can also model, if you see over the course of 90 days, this is a simulation of 90 days, you can also see that the target is actually moving a little bit and then it's jumping back again over time. And these simulations are done every 90 days, and there's a reason for that, because we're doing it highly realistic. So we simulate exactly how it is into space when we're actually orbiting in a 1-year orbit. We need to turn our spacecraft to realign the solar panels to power the spacecraft. And so, of course, for our simulation, also have to do that. So, if you want to see the camera to scale, here you have me next to it. And one of the things that I have been helping to improve in my PhD is to make this new toolkit that's called Plutonium. Plutonium is make it very easy to kind of make a new project and a huge simulation study on the fly within a few minutes, and expand the use case of Plato Sim just from one single camera and setting it up to do it for all 24 cameras, because of course we want to have a yield of the entire mission, not just one camera. And of course we feed back everything into our simulator, which is an open source pixel-based simulator here at Leuven. And we do that in collaboration with a lot of the teams that are also working on the justification, performance of the instrument and so on to make it as realistic as possible. And all this can be put on a supercomputing cluster, which I've been using a lot in my PhD, and you can get your simulations out after some reduction. But I already mentioned now the simulator, we have simulations as well, but what does actually mean to have mock simulations? What does that mean? Well, mock simulations is the next base case if you don't have real data. So here we are kind of like making an artificial object to inject into our simulations. So for us, mocking is basically creating a mock object, a light curve, which you've seen here, of a model of a star as it changes its light flux over time. And it could be anything, for example, like a solar-like star here with a transit of a planet. And we inject that into a pixel-based simulator. So that's essentially just testing the case where we don't have the real, the true observations that's coming in the future. We here have like a next best case where we know the ground truth, and we try to then recover the ground truth. So these simulations that I've been doing throughout my PhD are sort of in the regime of injection and retrieval exercises. So we inject something, and we then look for if we can, for example, in this case, can we recover the exoplanet transit? Or, for example, could we recover some of the stellar signal that we also inject in our simulations? So injection and retrieval exercises are quite important here in my PhD. So to give you some conclusion on the first kind of major work that we did for Plato Sim was to expand its use cases. And I want to highlight that Plato Sim is quite an advanced simulator. We can do a lot of different things with it. And it also simulates most of the products that we're interested in the future, both meta data, but also light curves and pixel images. And it's really been used quite a lot in the mission consortium of the mission so far. So I would say it's a quite indispensable tool. And it's our aid to continue now on this little talk here on the digital journey with some exploration of other type of sciences. And one of those sciences that I already mentioned is looking into the work package of pulsating stars. The work package of pulsating stars, as the title here suggests, doesn't really say anything here, exploration of stellar objects, but it is in fact on the pulsation of stars. And so I was sitting here 2 weeks ago listening to another defense where my supervisor asked me this question. And so this one is for you, Pierre. What is a star? I think also maybe the use of someone else as well. But in essence, it's just a giant ball of gas. It consists of hydrogen, helium, and in its core we have fusion going on. And I think most people will describe a star very simply between a balancing act between a radiation force or gas pressure from the outgoing energy, balanced perfectly with the amount of gravity we have from the star. So these stars can live for a very long time on what we call a main sequence, most of their lives, and I will show you in a bit how that actually looks like. So in essence, that's a star, yeah. So if we would take it a bit further and then look at the stellar evolution of stars, we can take a beautiful little observation from Hubble, for example, of a very, very big globular cluster where we cannot get a snapshot of all the stars we see in the sky here. And so we can do something clever. We can look at them, and then we can first divide them up in their color. And we know this is actually a proxy of the temperature on the surface. We call this effective temperature. And we can then also put them after their brightness. And so we get to the very famous diagram, some of you probably know of, which is called, some of you know of, sorry, it's called the Hertzsprung-Russell diagram, or the color magnitude diagram, where you have the stars in the diagonal live most of life on the main sequence. And then when they kind of exhausted the fuel in the core, they can move on to the red giant branch. And even further, other fusion generations can go all the way to horizontal branch stars. They're very blue. And in this project that I'm going to propose here in the future to you in this talk, I'm also working with these dead stars, which are called white dwarfs that you saw over here. So. Okay, so now we have the idea of what is a star. Then let's try to understand how stars pulsate, because this is quite the interesting part of this main project. We know that stars are pulsating, and most stars are actually variable to some extent. So let's look into that. Well, for 101 level of stellar pulsations, essentially you can think of it as a musical instrument, or could be here if your musical instrument is a glass of wine or water, and you have the right amount of water in your glass to have the favorable conditions to excite one of the modes here of the glass. You can think of the same of stars now, they're just 3D objects, right? But we just need favorable physical conditions inside them to excite some specific modes. And these modes are typically excited, or they are restored by force, and that can either be pressure, so that's the sound waves, for example, that I'm sending out to you in this room, where we have the medium of air in the room that is propagating the waves. And then we have also gravity waves, which are slightly more complicated, I think, for like in layman terms to explain, but I think the best way that I can imagine it is looking at the evening sky or morning sky when you see these beautiful ripples that you sometimes can see in this, the cloud layers, which is actually exerted by the gravity of the Earth and make these ripples. So that's sort of the waves that can propagate from the gravitational field of the Earth. We also have that inside stars, and so that's my good analogy to this. And one of the things we have learned so far, and why I actually highlight now stellar pulsations, it might seem a bit random, why would we focus specifically on that compared to all the other work packages so far? Well, it's actually not that random. It's because that stellar pulsation exists in this diagram we saw before with temperature or color and luminosity here, or the luminosity or absolute magnitude. We can see that stellar pulsations, they are everywhere. And especially this main sequence that I already alluded to here, that's where stars live most of their life. And that's also where we see that most of the stars are actually pulsating. There's a lot of different classes of pulsations here, which makes them extremely interesting. And the whole diagram as a whole is quite interesting to look into how the stars, they are pulsating. One thing that we also learned from this diagram is that immediately if you look at the sun here, which is just one solar mass, it has a certain temperature and luminosity. We can see as it moves and it gets older, exhausts its core fuel, it will move up the subgiant branch and the red giant branch. And at some point, you can see that it also moves all the way to the left here and becomes a white dwarf. So they're very compact objects at that star, at that point. But it's not completed, that's not to us astroseismologists at least, because it actually goes through other loops here where we can have stellar pulsations. And so the sun in the future will most likely have gravity waves, not the pressure waves that we're seeing it right now to have. All right, and the tool that we use for doing all of this science here is called astroseismology, and it's one of the most powerful tools we have in our little bag of exploration, because with astroseismology, we have now learned that we can pierce through the outer layers of the star. We can look into the star, how big it is, how massive it is, what is the chemical composition, and many more things like age as well. And this is really something that is extremely powerful in modern astrophysics. And so if you look at the pulsations of stars, this animation shows a few different so-called modes. So the very simplest case here is a radial mode. That's where the whole star is basically contracting and swelling, it's heating and cooling. And you can also have different other types of modes, of dipole modes or even higher degree modes. Some of these modes are very important for the astroseismology that we are doing and the modeling of these stars. I won't go too much in detail in this talk here because we don't really use it directly in this work. But I think it's a fun little animation to show. All right, so let's arrive to now the main topic of this little project here, which is MOCA. So MOCA is this Plato mock astroseismic catalog that we have been simulating. And what you see here is, again, this little visibility flower of Plato. Well, this flower is actually conducted from all the stars we have from another satellite called Gaia. We have the positions, and we have the brightnesses, and we also have the distances to most of these stars you see here. You can see the Milky Way is actually the darker spot you see there, and this is on nearby dwarf galaxy, the Large Magellanic Cloud. So this is the first Poynting field of Plato. What we did was looking into, now we had this color magnitude diagram, or Hirschman-Russell diagram I showed you before, how stars they live and die. And we can now take all the stars that are around within 3 to 4,000 light years from our own sun here. And we can look at all, well, from the satellite actually, but we can look at all the stars and we see some of the same features here. In our work, we specifically want to look at stars that are pulsating in a manner that's different from our sun. So we're looking at stars that are more massive, and all these ellipses here are approximate regions where we know that these stars will have certain types of pulsations. So we took every single of these ellipses and simulated their behavior in terms of simulations with pulsation injected. So that includes now some of the main sequence here, up here. That includes some of these non-radial G and P modes. We also have the classical pulsators. That's the ones you see in the two yellow here and the orange circles, or ellipses. And those are the ones that has more or less the radial modes, which we can use for distance measurements, but a bit less degree for astrosseismic modeling. And then we have the compact objects, these sort of dead stars, or hot subdwarf stars. So we, in this study, looked into only 2 classes of pulsating stars because it was a big job to do the analysis of everything, essentially. And to narrow it down a little bit was also that we knew that these stars are quite important for the mission. They are important for calibration of the mission, and also validation sample for the mission as a whole. If we look at these 2 stars that I have highlighted here, the Gamma Dorados and the slowly pulsating B stars, that's the SPB stars. These stars are very different from our sun because they actually, instead of having a convective only envelope here, what you see here with the waved shaded areas, that's where we have the energy transport of the star is happening with convection. So inside the core of these stars, we have convection. And that convection can actually overshoot into the radiative envelope. And that can bring new material into the star so the stars can live longer. And this is actually an ongoing, very challenging task to figure out exactly how this works. So that's one of the reasons why we are looking at them as well. The way that we specifically went forward with this analysis was looking at, again, our mock object, as you see here. The mock object is the orange idealized simulation that we inject into simulations with PhD. And then we simulate all the cameras and have a reduced light curve, which is the black points you see plotted on top. And one question we want to answer in this analysis was, when we do this injection and retrieval exercise, we have all these pulsation modes, and they have many, many different frequencies. So that's what you see in the bottom panel here. So if you take the frequency analysis of these stars, one single peak here corresponds to a single mode. And we wanted to know, injecting all these modes, how many could we actually retrieve? And can we retrieve enough to do some of this astrosseismic modeling that we're interested in for the future mission? If we look a bit more into this diagram, you can see that there's not completely a random order to these peaks here. And one of the powerful tools that we have is to create so-called period spacing pattern. So imagine now you take the distance between these 2 peaks here and you just plot it on the y-axis and you keep on doing it for every single peak. You get like a diagram here as a function of period. You can see that the modes are more or less equidistant along the row here. And we can learn a lot from the shape of this period spacing pattern that you see here in this diagram. That could be, for example, the rotation that is near the core. It could also be the chemical profile of the stars throughout the star. Okay, so with that, I need to introduce just a little term here in terms of coffee. Because Mocha, obviously, as the name suggests, has a bit of a theme. And I try to make a theme worthwhile. So what you see here is that I simulated 3 different realizations of the noise that we injected in simulations. So in the first case, it's more like an optimistic case, affogato, so crème de la crème, you can say, where you have basically a bit too optimistic case of your simulations, maybe not exactly what we would see in the future. Then you have a pessimistic case, we here called cortado, which is where we have upped the instrumental noise to a level where we might see something if the mission goes quite wrong in the future, let's say, or if we don't have the expected outcome of the mission as we would expect. Then we can now have a simulation set that will show a bit more how it would look like. Or we have the more realistic case now, where we injected for every single star that we simulated, not only the targets, but also all these contaminant stars, we injected a signal that is coherent to what that star looks like. So if it's, for example, a sun-like star, we will put in some stochastic oscillations, maybe some other pulsations as well, depending on which star exactly it was. Okay, so remember these names because they're going to be on the next figure, so that's why I put them here. It's maybe a bit easier to remember. So let's go to the results. One of the major results of, if I only look now, I said I was focusing on 2 types of stars. I will only show you for the slowly pulsating B stars here. And what you see here on the right is the flower that I explained to you before, right? That's the camera visibility. And then you have on the x-axis here, you have basically the brightness, how bright is the star, where this is in magnitude, so the lower the number, the brighter the star is. And what you sort of see here all through the landscape, if you look at the color bar, that's the detection efficiency of all the modes we have injected and how many we can then retrieve. So it's quite expected that we have the lowest noise when we have 24 cameras, and also when we have the brightest stars. In this case, of course, you see a gradient where almost 100% of all the modes are recovered, in this case, and you move sort of up to the upper right corner in this diagram here, where you can see almost none of the modes are detected. I think one of the good things that is to highlight by this diagram is that if we take a star like an SPB star or a Gamma Dorado star, these G-mode pulsating stars, around somewhere in the middle here of this diagram, we have more than 50% of all the modes that are recovered, which is quite valuable because that means that even with that, we can typically construct period spacing patterns. We can then do some astroseismic modeling, and we can learn something about the stars. So that's essentially the idea here. I also said that we looked at this Quattaro sample of stars, where we just upped the instrumental systematics. So now here we are looking now at the difference between the idealistic case and this case that was a bit pessimistic. And so you take in percentages, the difference, as you see from above. And so compared to the idealized case, we now don't really see a big difference in the simulations and the modes, the number of modes we can extract from our simulations in the bright regime or in the fade regime. But if you look somewhere in the middle here, we see that there's a big difference. And this big difference is actually a quite funny regime, because we know that this is where the stars itself are the most noisy things that we have in our simulations. The photon noise of a star is the most noisy thing you have in space. Yeah. So we know that this photon noise regime is completely destroyed by instrumental systematics, which is of course important to know when we will be flying in case of less good performance. Then we go to the case where we have the sample of Doppio. Doppio was this bit more realistic sample. And in this case, if we take the difference again between Affogato and Doppio, we see that there's not, luckily, much of a difference. There is a bit of a difference, obviously, but in this case, I would still argue and bring the argument that we can do astroseismic modeling to a high precision. And so we should not be so worried that every single star is variable, because that's what we should expect it to be anyway. One thing that I wanted to highlight here as a last thing in this study, out of many things we could have highlighted, is if you look at a diagram where we have now the precision for which we can extract these amplitudes of each of the pulsation modes, and we plot that on the y-axis here. And then on the x-axis, we now plot something that's called the stellar pollution ratio. You could think of it very easily as the kind of all the flux that comes from these nearby contaminant stars. How much of that is actually leaking into this little rectangular mask for which we extract the photometry from. And so what we found is that if you take this diagram, there is sort of like above a level of 6% leakage into the mask. We see a huge increase in the precision. So basically, you're getting worse and worse and worse. You cannot determine your amplitudes very precisely when we go above this level. But even though that I now talk about astroseismology, this level is actually quite important for the core science, because a lot of stars that will be analyzed on board the spacecraft and where we're going to be looking for exoplanets, this could well have a big effect. For example, in the case that we have a large pollution here, we might find that a Jupiter-sized planet could be mistaken for an Earth-sized transit, just by the level out of light that is contributing to this. So obviously it's important to know what this stellar pollution ratio is in the future, both for astroseismology, but also for the core science, I will say. So takeaways from this project here was that we are well capable of taking a simulator and potentially also in the future the spacecraft and look for pulsation modes in many different types of stars and find a spectrum of them. We can do that to a high precision, and we also found that we have this kind of a Goldilocks threshold where we see that there's a big difference in the precision we can get for the modes we extract. And we saw that if we look at if we compare the instrumental systematics compared to the stars or the simulations where all the stars are variable, then we see that the instrumental case where we have made that much worse is definitely the one that kind of overrules the noise budget as such. So with MOCA, we have been quite successful, let's say, to highlight some of the exploitation we can do with Plato, and I think this will be used hopefully in the future also for the guest observer proposals. But MOCA is not done here, right? Because we still have a full catalog of many other pulsating stars that haven't been analyzed. So we also need some experts to take over and look at this in the future. The very last project that I want to highlight here is the other work package now on the extragalactic science. And I say supermassive stellar objects. So you might already have guessed what those could be. So that's black holes or supermassive black holes. So supermassive black holes, or in general just black holes, you might know if you have read some relativity before, or at least some general science of relativity, that black holes are a very simple solution to Einstein's general relativity. Black holes are believed to form from actually stars itself. Most of the stars that we have, when we have a massive star, explode in the supernova explosion, and in the core of these stars we can leave behind a black hole. We know that black holes, when in the early days, the leading theory we have right now is that the more massive ones, so the massive black holes, are probably formed from seeds of very large stars. And over time, when these stars are formed in, let's say, irregular, smaller galaxies in early days of cosmic history, when we have aggregation of many galaxies forming to bigger and bigger galaxies, such as the Milky Way as we live in today, we have then the sinkhole of black holes falling into the center of these, and we can build larger and larger black holes until we get to what is called active galaxy, where the black holes are actually having so much material around them they can make jets and be visible throughout the universe. But if we continue this road, obviously, you can imagine now we have a galaxy with a supermassive black hole. We now have evidence also that the Milky Way is hosting one of such objects. But imagine now we have two large galaxies colliding together. So the video is sort of continuing here, and we might end up with what is called a supermassive black hole binary. So in this little simulation here, I want to highlight the kind of things that we are looking for in this project, which is the photometric signature of such objects. And if you look at the simulation here, and you take two supermassive black holes, we have, from the best theories so far, that these black holes should have an accretion disk, and they're very hot, these accretion disks. And they're sort of feeding into the black hole. And then over time, if you are in the right angle, as you just saw before from the video, you might have eclipses, just like when we have an exoplanet going in front of a star, or the moon going in front of the sun. But in this case, we have what is called gravitational lensing. So the objects here are so heavy that they're basically lensing all the light from the accretion disk of its neighboring black hole. And you see a huge intensity increase in your light curve and a magnification of the object. So this is something we can really see because it gives like a beautiful spike in your light curve over time. We also see other effects such that now the stars are moving around each other, and that gives rise to the phenomena of Doppler shift. In this case, we call it Doppler boosting because it's a relativistic effect where the light is basically of fast-moving matter is then boosted up and intensified. And the very last thing you might have seen throughout this video is that these accretion disks, they're actually not constant. They're not like a constant source of light. They're changing over time, and there's material falling into the black holes and accreting energy. And so this is actually a bit of a random process. We call this a stochastic process. And so this is a signal that is on top of all. Yeah. good, you still hear me. All right, so we set out a little project, I think, which will be very interesting for the future proposal of Plato, is finding Spiky instead of finding Nemo. So here we can look for Spiky because we know so far a very, very good candidate that was observed in the Kepler fields. So the Kepler Space Telescope found this beautiful, like you see over here, where you just had the three different kind of observational features. You have the spike from the gravitational self-lensing effect. You have this sinusoidal motion here, sinusoidal intensity profile, coming from the motion of the Doppler boosting. And then on top, you have all this variability here, which is stochastic, you can say, noise, or black hole binaries. So we know that we have a candidate. It hasn't been confirmed yet, but the good thing is that we also know that Kepler and Plato has an overlapping field. So we're going to be observing this in the future. And this is not in 2 years, unfortunately. This is more like a venue of around 4 years, because the north field of Plato is a bit further in the future after we are done with the first southern field. But we know we can observe it. And actually in this simulation here, I'll just show you one of the challenges that we have, which is we have the target right there. And we have another bright, maybe galaxy or a star next to it, and a lot of different types of objects here that might be galaxies as well, contaminating our mask, which is only 2 pixels in this case. But we know we can observe it, so we try to go ahead and then simulate it. And we also know that Spiky luckily is observed with 24 cameras. So the noise budget should be lower compared to having only 6, for example. And then what we did was simply taking the paper of this Hu et al., Hu and collaborators from 2020. We redid the physical models in the photometry signal. So you can see our regeneration model here. And then we injected that in our injection and retrieval exercise. And in this case, if we do the whole full end-to-end analysis of this object, we see something like this. So this is 24 cameras, and remember, we're really pushing Plato to the limit here, because Plato was never designed to do things that are this faint. It was only designed to do really, really bright stars to find exoplanets. So we are really playing with the noise and the fire, let's say. But it's still, even in a simulation like this, we are quite, I would say I'm quite optimistic right now, because from this simulation, it shows that without any kind of further analysis almost, we can see that such observation of Spiky will be able to confirm its nature, that it is actually a supermassive black hole binary. Now the question is, can we go further? Can we use Plato really for hunting down these supermassive black hole objects? And so here I'll just show you, if you take different brightnesses, magnitude here, from 16 up to 19, we can see that, well, if you're a human, maybe up to 18. But then if you want to go further from this analysis, we should probably use a machine to not bias ourselves. So this is the future goal of this analysis, to look into a much, much larger simulation set and see what we can kind of retrieve and can discover for these type of objects. And what we have done so far is collecting, actually, with a high confidence, all the active galaxies. These are typically called quasars. They are quite young galaxies, and they're very active, and he has these very, very heavy and large supermassive black holes in the center. And so what you see here is basically all the quasars that we have found from Gaia and a catalog, and we have put it into one single catalog of quasars that we might be able to hunt down in the future. So now the whole thing is to select the right ones that might be good candidates to find also supermassive black hole binaries, not only just a single black hole. So I want to finish off here in my talk, and with the conclusions that first, we have this beautiful simulator, Plato Sim, which I find a quite indispensable tool, obviously, because I've been working on it for 4 years, so so I hope that you find it too. But it's also an indispensable tool for the mission, because we really have been developing and making it better and better and better for specifically Plato. And I also quite a lot in the mission consortium. But obviously, we can use it for the exploration, which is the more fun part, I find. So we have done this by looking at actually, this is the largest simulated data set for the Plato Mission Consortium to date, where we have looked specifically at the work package of pulsating stars, and hopefully in near future simulations will or even analysis of these stars will. Yeah, still listening, yes. And then very lastly here, we have pushed beyond stellar pulsations, as Connie will say, and looked into the very faintest limits of Plato, and tried to see if we can actually confirm some of these supermassive black hole binaries. Obviously, there's much more to look into here for this specific work package. This was sort of a highlight of that. But I think overall, what we can conclude from this thesis is that, well, with Plato Sim and with these simulations that we are undertaking with doing injection and retrieval exercises, we can say that Plato complementary science will probably be quite successful with what we have on the horizon with a new space-based legacy from Plato. So with that, I want to thank you all for listening. So.
Thank you, Nicolas. Then we can move on to the next phase, that is the discussion of the work. But before starting the discussion, I want to introduce the members of the examination committee to you. So this work had 3 promoters, all affiliated with the Institute of Astronomy of the Department of Physics and Astronomy at KU Leuven. We have Professor Connie Aerts, and there is Dr. Joris de Ridder and Dr. Pierre Royer. Then the other members of the jury, so there's 2 more members from the Institute of Astronomy, that is Dr. Andrew Tchenko and Professor Denis de Vrije. And then last but not least, there were 2 external members in this jury. We have here with us Professor Hans Jannsen from Aarhus University in Denmark. And then, online we have also with us Professor Magali Deleuil from the Laboratoire Astrophysique de Marseille in France. And my name is Ewald Jannsen. I'm from the Quantum Solid State Division of the Department of Physics and Astronomy here at KU Leuven. A very short, for those of you who are not so familiar with PhD defenses at the KU Leuven. So these defenses happen in 2 phases. So there was a closed meeting, the so-called preliminary defense, that took place a bit more than a month ago, I think. That's a closed meeting with all the jury members present, and then there was an intense discussion, or a tough discussion, not intense. There was a real discussion about the work.
Heated.
In-depth discussion. And at the end of the meeting, there was decided that the work can be publicly defended, so the positive outcome. Otherwise, this meeting would not have taken place. And so now today is the public defense. The jury will again ask questions that can be points that were not conclusive maybe at the previous meeting. It can also be new questions, or it can be some broader questions that go a bit outside the work as well. And at the end of those questions, also you, the public, will have the chance to ask questions, because this is evidently public defense. Okay, I suggest we start in Marseille with Magali, please.
So thank you very much for this introduction. Thank you, Nicolas, for your presentation. Unfortunately, I can't be with you in person, and I definitely regret this. All the more reason to say how much I appreciate Nicolas' manuscript, and especially the work he put into it. I would like to emphasize Nicolas' work was central to the Plato mission, and that also you did a lot of work to help the community to prepare for future data. And you did that with kindness and very effective support. So I want to thank you for that, because I benefited it as well. So your presentation gives us just some short highlights to all the huge work you have done. And in particular, you made Plato Sim easy to use, with which is not because listening to you, it looks very trivial, but it's not at all. And yeah, it's true that Plato is going to be a very complex instrument, and you made for the regular scientist something easy to use, in fact. So I think your presentation on all stellar effects that will challenge transit detection is a very good summary, and it's, well, even if today it was not maybe very obvious for the regular public, it's true that at least your manuscript show all the issues that we're going to face. So on a general level, you mentioned that Plato will perform aperture photometry, and you just said that, well, it's going to be something easy. You take the pixels and you just go at them. So it's not that simple indeed. Can you give us a brief summary on how the pixels will be chosen and how it will be done, in fact?
Yes, of course I can. Let's go a bit back to a slide that's a bit more relevant, I guess. We can take whatever, doesn't matter so much. Okay, so yes, sorry. Let me go out of the slides, it's probably easier. Ta-da! Oh. No. There we go. No. All right. Future challenges here. Let's, this is not the right one. Sorry, I think the whole slideshow just went down, so let's open it again. There we go. Sorry for that. So it's indeed true that the aperture photometry, I just mentioned it very quickly. Did I not stream? What the?
I didn't expect it's going to be
Okay,
such a
yes.
tweak.
The question is so difficult, Mackley. So.
So sorry.
Okay, so this was the slide I was trying to get to. Okay, after a little while. Okay, so is it true that if you have aperture photometry, it might seem a bit simple. I only show you two different cases here, where you can either do the aperture photometry or the PSF photometry. But obviously, if you now take this very simple aperture photometry technique, it's not really that simple because you need to select the right pixels. So you can see this mask has a lot of different little squares here. Each of them is what we call a pixel, and we can sort of sum up the lights inside of them. But selecting them is not that trivial. And actually what Plato is doing here in this case, it's an algorithm that's been developed by a guy called Macquarie. And Macquarie, he was looking into how can we optimize the stellar signal of this transiting signature that we get if you have a star and we see a transiting planet. And how can we also at the same time avoid all of these stars that are nearby here. So this algorithm is not just as simple that you can sit there with your mouse and you can click which pixels you want, because all of this is autonomous on board the spacecraft. It has to do the selection itself. And so what it does here, it makes a balancing act between how much can it take in the light to increase the signal, lower the noise, and how much can it then avoid nearby stars also. This algorithm is quite complicated, and it uses the stellar pollution ratio, which I showed you later in the talk. It uses that as an input, as a specific feature when you do the extraction. Then on top of all of this, obviously, this is just the extraction. Now, you might see these light curves, they look almost good, but in fact, they are not. And you can also see here that we have a little jump here of the lights, and that's simply because in the algorithm, there's also a little method where we can select or deselect a pixel. And when we have that, then we might end up with maybe some jumps in our light curve, but we have still the optimal signal to noise in our light curves. Then on top of all of that, now you have your light curve for one single camera, let's say, and that's only for 90 days. Then you can have, of course, light curves for all 2 years. That amounts to 8 quarters, and each of them will be having some strange behavior in them. And so what I have been spending quite a lot of time on in my thesis is actually developing methods that can take your data raw and put it to a reduced level where we know that we have a signal that we're looking for of the star or the planet, the supermassive black hole, and that is recovered, is still in there. And we don't remove that when we do some fancy algorithms to detrend our data, for example. So the whole photometry pipeline, for example, for the space mission of Plato is quite complicated in this sense. So we have a lot of steps. And then obviously, yeah, you have the other method, which I didn't touch upon, but that's your expertise, Magali, on the PSF photometry. And that is essentially the same, but now we can sort of indicate where we have contaminating stars, we can separate them, and we can model them independently in the same go, and we get, instead of just one light curve, for example, here we have the blended signal of two different stars. But in this case, for example, we can deblend them, and we can get the signal for each of the stars to typically a much higher precision than we can do if we just have the general aperture photometry technique. And in between of all of this, you can do a combination of it. So actually, Plato is using a combination of PSF. It uses the high resolution PSF, the instrumental profile of a star on the detector, to kind of make these decisions about which pixel they should choose or deselect and so on. So it's quite complicated, but yeah, I didn't write those algorithms, so I didn't mention that much.
Okay, thank you. There is another aspect which is not included in Plato Sim, unless I'm wrong, but which challenges transit detection for, well, with Kepler or Corot and so on, which are telegraphic pixels.
Yes.
How do you see that? Would it be interesting to include that in the simulator? And do you think that for stars, that because of the multi-camera approach, that will mitigate or not this kind of effect?
I would say so. I know that these pixels that we are talking about here, when we look at the detector for the general audience, if you take a single pixel, there might be at some point light coming from this pixel, and some other times might be a lot of not so much light. And so this is to do with the specific electronics, that the gain is changing over time, and I can suddenly pump up the level and lower the level, and that actually in the light curve will be huge jumps as well. And it might be, if it's the right periods, looking exactly like an exoplanet transit, you might get this little dip. But what I know from the mission parameter database so far is that if you look at the percentage of pixels that should be such telegraphic pixels, the chance of you having one of your masks in one of them is very low. So I would say like it's a lower effect to take into account in Plato Sim compared to many of the other things that we also have in our pipeline. But it's an important effect, obviously, and it will also challenge your data reduction. But I would say for most cases, if you look at the Kepler mission, for those you saw like a complete level either was jumping up and down immediately, or it was as a constant level for several days and then it would change. That's at least the data I have seen for Kepler. So I don't think it's going to be a challenge as such for the exoplanet community. I think it's going to be more like a challenge for the calibration of the data itself.
Okay. And so for you, what would be the main critical instrumental effect to implement, I would say, in Plato Sim to prepare at best for future data analysis?
It's a good question, I'll say, actually. I think one of the things that I would like to see implemented, because this is one of the key points that I think in the pipeline for, is the fact that the thermal profile of a spacecraft is not really accounted for properly in any sense, in any simulation I've done so far with Plato Sim. And so what I mean by that is that when you have any rotation or any repointing of the spacecraft, you essentially change the entire thermal profile of the spacecraft. What that does is that it will, after 90 days when you have rotated, you're looking now at the stars from a different angle, obviously, and so all your cameras, they will start to drift over the field with a different kind of pace, different direction, and so this is quite important to take into account. But there's also another important effect, which is also something that is related to the gain of the detectors, which is when you heat up the spacecraft from a certain angle, you might change the gain of the detectors. And what we saw in the light curves of Kepler, for example, which is not something we have done ever with Plato, is that after a gap, when you have a repointing of the spacecraft, which is basically either every 90 days or if the spacecraft have to go into a safe mode or something like that, you see that the flux level is jumping up quickly, and then there is an exponential decay. And there's no, so far, simulation that does that, and there's no pipeline that takes that into account. So that, I think, if no one is thinking about it, it is something we will have to do on the fly when the data is coming. But I think we should do that now, take that into account for the pipeline. If we only talk about the pipeline, I think for my simulations, it doesn't matter so much because it's fairly easy calibratable if you want to take it into account. But yeah, pipeline-wise, I think it's important.
Yeah, thank you. I think it's interesting and might be worth indeed implementing this kind of effect just to get prepared.
Yeah, I agree.
Okay. And so if we move to the variable stars you have studies for gamma DOR or SPB sample. Yeah. Okay, so I have a couple of, how would I say, ignorant questions, of course, because it's not at all my field of research, but would there be any interest to perform a per camera or camera group frequency analysis, or you don't care, you just take the average light curve? I mean, there's some systematics.
Yeah.
Okay.
It's a very good question. It will depend on a bit what kind of data products that you are asking for, because I guess if we're doing the onboard analysis, obviously we can get all the cameras separated for a light curve, and I think in that case that would be very interesting. There is indeed also a time shift. So I showed you the spacecraft has these 4 groups basically, and there is actually a time shift between the cameras of around 6.25 seconds. So we could use that on top of the individual light curves, maybe to learn something about the stellar signal. In fact, that is something that I know that is one of my collaborators, James McCormick, he's also doing that. He's looking at specifically for the detrending. He's looking at, can we separate the real stellar signal from the instrumental signal in each of the light curves? And that's actually how you create the detrending in the first place. But for seismology, I think it will be very, very valuable too, because now you can start to play with also mode identification, I think. So if you have a handle on the different type of cameras you are looking from and the timing of those, maybe that will be possible. But I haven't done that myself, so I'm not entirely sure how efficient this will be to do such a thing.
Okay. So related to this kind of stars, you also said, I think it was when you investigated the contamination with solar-like stars, and you wrote that, or you took as an example sun-like stars with just 4% spot coverage. It looks to me that 4% is not that much.
You mean in the pieces itself, the paper, the plot that I showed?
Yes.
Yeah, okay. So that was a random sort of a realization of a more active star. But you say it's not too much.
Yes, I think. Well, I would like to know whether it's well, where does this number come from? Is it something you expect for the regular sun, or is it representative of the sun-like population or active stars?
Yeah. Actually, so that entire software that does these modulations of star spots. So for the general audience, we have sun-like stars that also have actually magnetic spots. They can have like sunspots. You've probably seen if you took some beautiful images of the sun during an eclipse. After or before in an H-alpha filter. But essentially what is important is that these models that we use to kind of simulate a mock object of a sun-like star with spots, they are taken from not a sun, actually they're taken from the Kepler mission, We're using realistic distribution of the spot's coverage, and also the periods, the kind of activity level that you see from different indicators, such as the calcium lines, H and K. And so all of this is linked together with the initial period that you draw from the rotation of the star. That's the core of the software, how it works. It will draw that parameter, and then it will select which color is the star, which we get from real star catalogs like Gaia. And then you can then trace forward in this simulation and from a random distribution, what is the kind of activity level we will get. The plot that I showed in the thesis is completely random. It doesn't have an underlying meaning as such. It was just to show the software. Sometimes we have some stars that almost have no spots over a period of 2 years. And that makes a lot of sense because stars, they have spot modulation from up to 20, maybe even 50 years sometimes. So obviously our sun is around 11 years, or even twice that if you take the magnetic shift of the poles. But you just saw the simulations where I hand-plucked a star where I wanted to show there was a nice spot. So there's no specific meaning, but there is a physical underlying model that is drawn from the Kepler survey.
Okay.
Yeah.
Okay. Thank you very much. And so for these, you shown that from your simulations, the stellar contamination doesn't play a major role for onboard photometry if the third light is less than 6%. Yes.
Yeah.
And so will the particular photometry of Plato, because we can see on your plot that there are still a number of stars which are above this threshold. So will the particular photometry with centroids, double aperture, and so on would help the scientific analysis in case of highly contaminated stars?
You mean compared to using the PSF photometry?
Or using the because it's onboard photometry, if I remember correctly. Okay, so if you have for onboard photometry, would that help?
Yeah, you're asking if you have more information about the different stars in the field of view, if that actually will help your photometry here in this case. To some degree, yes, I would say it depends a little bit what you're looking at. I mean, if you know the exact positions of your star, and you know, like from this is actually how it measures the stellar pollution ratio is calculated. It uses the positions and the amount of light from the PSF that we have determined, how much is spilling into the mask. If we have that knowledge, of course, we can do the backward calculation, and I'll say in the case of an exoplanet, we thought it might be an Earth-like planet, but we know that the signal has been completely depressed by contamination. So in fact, what we're looking at could be recalculated back to a Jupiter-sized transit. So it was a Jupiter-sized planet we found, not an Earth-like planet. And of course, that's also the same case for pulsating stars. In my case, obviously, we can also, using this threshold, I would say is very useful because we know how much that suppress the amplitudes of our modes. So we can actually go back and calculate what is the unsuppressed amplitudes of our modes. Right now, in my analysis, we don't really use that because we can do astrosseismology purely just by the frequencies. But if you want to do a bit more advanced astrosseismic modeling, we would like to know the amplitudes too. So I think this is going to be, for Plato, quite important, probably in the future when we have new techniques to go forward with astrosseismic modeling.
Okay, well, I was thinking also to ways to identify that the source of your detected modes are not the target, or is not the target, but might be a contaminant as well.
Yeah. Okay. Yeah. In the case where they're variable. Yeah. Yeah. That's a bit more difficult to disentangle, right? Because unless you really would do follow-up observations, you would actually never really know the truth, I think. You can, of course, you can try if you would have, let's say, out of a sample of stars, you have the onboard photometry, but then for some of them, you might then take the pixel data, and then you can look at the individual pixels, and you can look at the difference in the light curves, and you can kind of already disentangle in that way. But on a basis where you just have this mask, this is the simple measure how much light is inside these 4 pixels here. You are a bit in the dark because you will never really know that unless you do a follow-up observation. You can maybe do some kind of like disentangling, knowing what star that you have from Gaia, what kind of stars are nearby as well, and then you can kind of figure out which of the signals are not coming from this target. If it, for example, is a D star or spectral type, it might have the pulsation of SPB, and we know the other two stars, they having stochastic oscillations like a sun, and we see all these signals on top of each other. We can of course disentangle that. But let's say we have two stars of the same spectral type. I think that's going to be very difficult to, on top of just finding also the modes, but also disentangle the two stars. I think you would need more information in that case. Is
Okay.
my best guess.
Okay, thank you. Maybe some last comment on the gravitational lensing, which I'm not at all familiar with that, but so how much PK is representative of the QSO, and which kind finally of analysis do you foresee for a clear QSO identification?
Yeah, so it's a good question. So I would say when we have this spike from the gravitational self-lensing effect, that is the smoking gun, because we don't really have any other phenomena that can reproduce this. If we keep seeing a repeating signal from this, we know that these objects by like a high degree must be a quasar. We can measure the distances. And we have, on top of that, let's say, we will probably also have a Doppler boosting effect in the figure as you've seen over here. Then on the right, you would for sure know that this would be like a supermassive black hole binary. There's not a lot of other objects that can do exactly this, because remember that when you have a system of two supermassive black hole binaries, the self-lensing effect creates a symmetric peak. So even though that we might imagine that we could have a nearby star that could have flares, those are not symmetric. So if we would have high enough precision data, we could actually disentangle those two. So I think this, I would give my best guess to, I would not say anything is a supermassive black hole unless I saw a spiky kind of case, I think. Because yeah, we will for sure in all of them, if we take Plato and observe this catalog of supermassive black hole binaries that, or quasars that I have assembled, we'll probably see the stochastic variability in all of them. But the question is, would we see this Doppler boosting, and would we also see the peak? That's a bit more, yeah. Depends also on the underlying physical nature of these objects, if they actually are in our data sets. And that's another challenge on top of the simulations, of course, to answer.
Okay, that's well, very impressive, because I wouldn't have bet the possibility to observe the magnitude 17 and something with Plato. So, well, I hope you will not have too many in the field, because they will pollute the transit detection. But
Yeah,
something else. Okay, so I think I'm going to stop here. I want to thank you again and congratulate you for the good job you have done. Thank you.
Thank you, Megley.
Thank you. Then we move on to Professor Jannsen.
Thanks a lot. Let me first just continue where Magali was starting, namely, I'm really happy to see this work. I congratulate you with all that detailed work, and I'm pleased to and honored to be part of the committee to read this, and also the discussion we had in the first part of this, of course, did not reflect that it was many errors or whatever. That's not the reason that we had a long discussion, but we were really excited about the results and also the consequence of your studies for understanding much better or the link to the mission. And I had detailed questions also in the first part, and I'm not going to repeat all these things. I will get into some of the more general aspects of your study in connection to the mission. Also, in the future, when the mission flies and deliver good data, we will, of course, maybe go back to the things you did to better understand understand the data. So I think it's also in that context very important. But let me start with the science. The reason that Kepler was, of course, successfully selected is in this field of exoplanet research, and specifically here also combined with the study of stars and astroseismology.
Yeah.
But you showed a diagram on one of your earliest slides where you pointed out the existing exoplanets we have as a motivation for what Plato should do. And you gave I know it's a sketch, your circle there, but between 100 and 10,000 days in sizes of planets that are getting down to Mars. What is the reason that that there's a realistic hope that we will see these kind of planets in Plato, since we did not see them in Kepler?
It's a very good question. Also, a bit ironically, because the circle, of course, extends far beyond the mission duration.
Yeah.
So, but actually, the reason why I put it like that is, and it's linked to the study we had together with Macaulay and another student that did some machine learning to find modern transits, which is very successful doing for planets that are the size of the Earth, for example. So, at least in periods, we have tested with simulations with Plato Sim in the same collaboration study with Macaulay and the student, that we could actually recover these modern transits even up to far beyond. It doesn't really matter what the periods actually is. It doesn't care. The algorithm can do so very efficiently for an Earth-like planet with a Sun-like star. Then, yeah, I mean, you ask if compared to Kepler, what is actually the difference really here? So I would say, so there was something I didn't highlight in this talk, obviously, but Kepler was looking along the Orion spur arm of the Milky Way, and it was doing in the beautiful constellation of the Swan. But it had quite a limited, first of all, had limited field of view. It's not that we actually are having more stars in Plato. We actually have the same amount of stars, but now the field of view is opened up. So we can select, if I can get this to work again. All right, so we can select more stars that are more in the prime sample that we want to look for. So these stars that have a spectral type between F5 to K7 or something like that. And so in this case, we can also go much brighter. So I would say that's the main difference of the mission. So both, we will have the same precision more or less as Kepler, but our targets are much brighter. So that means that we can follow up the targets with radial velocity to a much higher degree. So if we even had a candidate, I mean, since Kepler was flying, we also have better algorithms, I would dare to say, in the exoplanet community to go and hunt for transits. We have better methods. But I think it's really the radial velocity follow-up that's going to be the definite proof that we can now finally get a measure of the mass of these planets and actually know also if they are real or not, if they are there in the data. So I think that's a real game changer. And we have a full network that is incorporated in the mission. It's not just like random telescopes. We actually have a network of people in working for the ESA mission here for Plato that will be organizing this. And that wasn't organized by Kepler because Kepler was much more, it was the data you can do and publish, obviously, and there was a community that was working on it together, but there was less collaboration from the very beginning, I think. Not that I think that I think the community was fantastic. So knowing the community, so I think we did really well. But I think you're still right. I am myself doubtful, I would say, because I know that sun-like stars are not like a sun. They're much more variable, and I think we will have a challenge there for sure.
Yeah.
So I hope with newer algorithms and with a bigger field of view or some dedicated targets where we can do PSF photometry, we will have the chance to actually find some of these rocky-sized Earth-like planets. But I won't bet anything right now. I will just say that that's a good guess from my side.
I mean, what you say is that it's not just let's be better argument. It's also that you have good reasons to think that at least some of these. But I'm quite excited about these very long periods because that, of course, they are rare because the probability of having any transit throughout the mission. But since you observe so many stars, we may see them. Then astroseismology. why is astroseismology going to be so much better? I agree with that actually, but so much better than what we could do in Kepler. Where is it that we can do better things in Plato than we could in Kepler?
Yeah. I think precision-wise, we will have more or less the same precision. I don't think we are going to do much better for seismology in general, because if you look at these curves of signal to noise against magnitude, we are more or less the same level, just much fainter. I think maybe again that could be coming from the fact that, well, we will have the same light curves more or less for the stars. These stars will be more or less the same spectral type, but a lot of the astroseismic parameters that we maybe got in the past, and maybe again couldn't be followed up with the other observations. And I know that radial velocity method is a quite powerful method to do also astroseismology and other smaller networks like the one we have in Denmark and Aarhus University, where I studied my undergraduates. And so those could also help to maybe improve the situation for star-by-star basis. But I don't think I have maybe a better answer to say that. I think that radial velocity, the photometry itself, I didn't know actually if that's would be improved. I thought it would be exactly the same.
That's true, but the sampling is so much better.
Yeah, okay, yes, true. For
So
solar like stars,
there were
yes.
so few stars we could really go to high frequencies.
That's true. Yeah.
Because the mission was not designed for that. So
yeah,
this time it was taken in immediately from the start. So,
yeah.
So then. And and then of course all the extra science you were talking about, and you did a very nice study on a specific case with this black hole. How many of those do you actually expect to see?
Yeah, that's also a very good question. That's why I think this study will be interesting to. We have around 12,000 quasars that we have gathered in this catalog, and we know to high confidence that will be there. But obviously, we also know that supermassive black holes, well, they are probably there in every single quasar. Are there binaries? That's a good uncertainty. And then on top of that, of course, as we already discussed, we want to have the ones that are perfectly aligned to the line of sights. And that is a much lower probability. So even in the field of view with 12,000, we might only have 10 or something like that, a handful. And so that's going to be the main challenge actually about this proposal. So if we're going to propose it, are we selecting the right ones?
Yeah.
And so that I don't have a good answer for right now, but hopefully in a year I will be better off to give you some estimates of what is really needed to do this. We can already rule out, I would say, like now Spiky was sort of like a good dead case where we already know that we saw that in Kepler. Yeah. We should acquire the pixel data for that and do some PSF photometry and really confirm this one. We know it's there, right? So, but I think for the rest, we of course don't know. We don't know the periods, and we might be unlucky not even to observe the spiky-like feature. So I can't give an indefinite answer about what we're going to do, but I think there's some challenges we need to see through for sure.
So of course you used this opportunity to study this special case, but there's also a community working on.
Yeah, that's true.
So I hope and guess they are very well aware that these possibilities are there. So and I assume you have a discussion with these groups.
So far we didn't. I didn't have a discussion. Maybe Andrew was involved here, but we haven't had yet to open the Pandora's box of these discoveries. I think so. But I think it's a very good point. And I would say like we have this new survey, the LSST, coming up with a ground-based survey, which is going to look at thousands and thousands of like quasars and galactic objects. And of course, like having some kind of idea from maybe that survey, which already will start in 1 year from now, will be already a huge benefit and starting point. So collaboration with people that work on that, I think, is like really beneficial.
So from your study of sensitivity to many of these things, including the black holes, but lots of other things like exoplanets, pulsation modes. What would you, and you don't have to be political here, but or what would you recommend us to do when we are in space concerning the future of this mission? Should we just stay where we are for as long as the mission will work, or what do we actually from the simulations can say anything about what do we gain from a new field, and what do we lose?
Yeah. I think obviously what we could gain is that, well, Plato in the first place was actually designed not to just be another photometer detecting planets. We want to characterize them.
Yeah.
I think that's one of the best ways to say that we should just stay. We should keep staring at the same place so we get more data, more precise data, and do better physics analysis of the underlying understanding of stars, planets, and so on. Supermass black holes, maybe if we stay there. I mean, in the case of supermass black hole, it's obvious, right? The longer we can stay, the more we can cover that baseline. That will be better for us, obviously. I think obviously we lose targets. Like that's the whole compromise for Plato was in the first place that we need enough stars that are sun-like to have that kind of estimates. Can we find another Earth-like planet? And so that was a bit, I would say, a bit vague discussion from now the political side of it, right? But if that's like scientifically the truth, but also what are we actually losing from not just staring 4 years? And so I would say I would stare 4 years at least, and then maybe even longer if we could. But I guess from the point of view, which was the scientific requirements of the mission, there it made more sense to, at least from a statistical point of view, to go for 2 + 2.
Yeah.
So, but we lose obviously targets by doing this. We could have found many more Gamma Dorados pulsators by having 2 fields, but we could not have studied those we found in more detail then. So it's like quality over quantity, I would say, a little bit in this case.
Yeah. So a trade-off, of course. So let me then go to this photometry. And I'm very impressed, of course, by the PSF photometry you show here, which clearly indicate that, I know it's a graph, but it indicates the possibilities. So this is excellent. The fields you show here as an example, is this typical for what we expect?
The features you mean?
No, that is
the variable
a bright star and then a faint star next to it. So is this a case we will also this jump you see? Is that something you expect we will find in most of the aperture photometry data? Will it typically? I mean, of course, there's an eclipsing binary there next to it. That's not necessary, but there's a variable star.
Yeah.
Stars are variable, whatever. This contamination will it be as huge as you see here on most aperture photometry from your simulations? So.
If it would be as big as this, or I mean, in most cases, not really, but it really depends on what we are talking about. Because for the main mission, those stars are selected to have almost no contaminants in the first place. Yeah. So that's also one of the ways you throw out some of the stars and the compromise of how much contamination they already have. That's the core science of Plato, the P1 symbol. Then, of course, you have all the P5, which is a bit more less selective. And there you will probably have many cases where you have a contaminant star that are almost as bright as the main target. Depending, that catalog is, let's say, less refined. But then we go to the catalogs that we have been looking at, and there I have even been less refined because I didn't even put a requirement on the targets. I put more a requirement on the data from Gaia that I wanted to know, are these parameters better estimated? And I took those stars that are the best in that kind of sense. So that could easily have many stars that are quite...
But you will find many stars where you don't have the problem. So you will see that the photometry in the 2 cases, which is good, of course, are similar. Yeah. But you can, and of course, you will get both. You don't have to.
Exactly. Yeah. For the prime targets, you can just do the both.
This jump you see there, I also assume you will know that something changed there, so it's not a surprise.
Yeah.
But there are, of course, people in the field or the researchers and students around that will like to get into fields where it's even worse than this. For example, those that work on clusters. Yeah. Do you see, will PSF photometry actually solve part of that problem, and to what degree, how crowded, when it becomes crowded, is there a limit you can say, this is hopeless, don't go that route?
Yeah. It's a good question because obviously PSF photometry will be for sure far better than aperture photometry in this case. If you have, let's say, 20 stars in the same mask and they all, like 3 of them are binaries, sure, you are a bit in the lost case. But it really depends on the crouching metric, I think. I don't know the numbers, but I think this is part of the algorithm that was developed for Plato. That's, for example, we had the discussion in the closed door examination where we know that if we within like 0.2 pixels and the star is relatively bright, maybe around like 5 times fainter, then we are really like playing with fire, right? And then that's the difficult case. So if you have an open cluster or like a global cluster where you have a lot of, let's say, faint stars, you could maybe expect them to be backgrounds, and then the rest could be a bit more bright. But I would say, yeah, it solves the problem partly, but not fully, right? In the case of clusters, like crowded fields, and as you saw even for spiky when we were observing it, it's not going to solve it fully. No, for sure. Yeah. So the question, I think that will be an interesting case to have the pixel data, so that we can compare and say, because if the stars or the galaxies nearby are not variable, then we can be a bit more lucky maybe in that case.
So what if we also, which is another group of people, go in the way of saturated stars? Have you simulated this to some degree, and where are the limits for how bright we can go based on your simulations?
Yeah, did I have a... I don't think I have maybe a diagram showing exactly... maybe I do, actually. Do I dare? That's the question. To go all the way down.
I dare.
Yeah, so I have like a little backup slide here. Okay, so it doesn't show all the way in the bright limit here, but so here we see the noise profile of our cameras as a function of magnitude. We have this visibility flower dividing them into 4 tracks. And you're asking about the very faint, very bright limit here, which is actually beyond this, as you see on the left here. We know that the Plato detector will, well, depending on what you put in as the gain and the kind of like parameters, we know around like 7.5, 8 magnitude, we are saturating the CCD. Then there is a regime until where you start splitting flux out of the imagettes. And that's the sort of the worst case, let's say for on-board photometry, because we cannot do anything about it. Then we lose flux, we lose our precision. There's no way to go beyond it. Then we have to expand it, and we can do that with some other mask. We just put more images on top of each other in a long column. And the reason is because when we do the simulations, we have spilling of flux in a vertical line away from the central points. PlatoSim, I didn't use it in the bright limit. We already discussed this. PlatoSim is not as realistic as it should be in the bright limit. We have many flaws, I would say, there. And one of them is we don't take into account the interpixel sensitivity properly. And that interplays really with the stability of the spacecraft. And we are doing way too good for what we should account for here. But we also have other things like, for example, the saturation right now is symmetric. And we know from the detectors that the way that they're glued together, there is some borders where basically the flux stops and then it starts spilling much more in the other direction than one direction. So we haven't accounted for that yet in our simulations. So people that do saturated star photometry, they have a lot of things to look out for, I'll say. So, but it's doable. I mean, we need more development on the simulator.
So I will just, I have one more technical question and then a broad one as my last question. So the technical one is actually the link to what you just said, namely that there are some, in the simulator, some assumption about intrapixel. Maybe you can tell here what are interpixel actually, and then is it simulated correctly in the simulator, or are there limits here where we...
Which effect, sorry, I didn't get it.
The intrapixel.
Intrapixel, yeah. No, it's not simulated correctly right now, perfectly, because what you can imagine when you make like a pixel-based simulator, we have all these pixels, but of course we are modeling electrostatic potentials and essentially the sensitivity, how the photons are coming into the substrate, and then basically getting down and detected. And in principle, you should take each of the little pixels in your fields, and you should model them. Let's find me a good little image of that. So let's go back to this one. No touching the others. So if you want to do this realistically, we need to take each of these small pixels and split it up to a sub-pixel grid. That's the insta-pixel sort of sensitivity you can inject there. But in many of the simulations we do, it depends really on kind of also the models we're using for the the point spread function, the model of the stars that we are getting through the instrument. There is a way to actually use a simulation where you can split in the pixels to very, very small pieces very accurately. But then the problem is still the underlying model below it doesn't account for the variation of the sensitivity all over the pixel itself. And so we need actually real data from some of the test houses and cameras to take this into account properly, I would say. This is something we should, well, this is something that the people that work on saturated stars should do, because if they don't, they will get the results that are not realistic. Yes.
The simulator allows it in principle.
The simulator can allow it. Well, we need to implement.
Of course, it's not better than the information you put into it. So.
Yeah. Because now we use just a different model for it right now, where we take a sensitivity variation over the field per pixel, but not the interpixel. Really.
Okay. Yeah. So my looking into the future question, when the mission flies in, hopefully launched in December next year, and you will start to get data. How do you see the role of your study here and the possibility to use the simulator, Plato Sim, in assessing the quality of the data, and specifically if you see things in the real data that you don't understand?
Yeah, I think, well, the obvious case is obviously when you take the example of Hubble. I mean, if you have a spacecraft that fails for its main purpose, for labor focus or other things, you can kind of simulate why it looks like it looks wrong, like so you already have an idea. But let's say that in the case that Plato are really performing as expected, then I think it's gonna be useful but difficult to implement some of these things, because real data has much more noise and other funny features that we would never really know of before we are in space. So those ones we might be able to simulate when we know them, and then we can use that information to mitigate and make models on ground that we can inject, send it up to spacecraft, and then will be implemented sort of on the onboard software. But I think that's going to be the main use case of Plato Sim when we're running, or in this case, for example, we can, obviously what I'm doing here, exploitation. If you still are in the complementary science consortium, are interested in the new science project, and you're before the next deadline where we're going to look at the other fields, if that's going to happen in the north, then obviously simulations are the way to go, even during the mission, I would say.
So, Nicholas, what would you like to work on in Plato when it flies? What are you most excited about to see?
I'm pretty excited about this. I would like to see this to end this supermassive black hole binary project, even though that we might not find that many. I think it's a pretty cool project and something I haven't worked on so much in the past. But I think also we had a small discussion at the dinner after my internal defense, and I'm pretty excited about exomoons. Like I think we are on the verge of finding the first moons, which is outside our own solar system. We haven't found any. We know that in our solar system we have more than 100, for example, so maybe a few hundreds. I think that would be a really cool case to finally go back to look at the architecture of a solar system like our own and reflect upon how it was formed and some of the key findings we see there. And for example, the question of life, because we, for example, know that the moon is not captured, but actually collided into our prehistoric Earth. And we have no idea if that actually sets the scene for life as we know it. So I think those questions can be linked back quite a lot to exomoons.
Exciting, thanks a lot.
Hi, Nicholas. First of all, I would like to join my colleagues and congratulate you. That was really an excellent presentation. It was also an excellent manuscript. One of the best I have the chance to read. I know this kind of simulation work is really difficult. You have a lot of things to take into account, a lot of parameters and things to consider, assumptions, and it's a lot of work, and you did it really, really well. I have a couple of questions. And the first one, I would like to come back to the first question of Hans here about the putting Plato in the context of asteroseismology and the context of other missions. And I would like to go a little bit further and ask you, science-wise, what is the big science question in asteroseismology that Plato will tackle that was not possible, for instance, with Kepler?
So yeah, for the core science you mean, or for what I've been working on? That's two.
For asteroseismology. in
For
general,
asteroseismology as a whole. Yeah, that's a good large question. I think so. What we know from asteroseismology, if we just now take the case of sun-like stars, obviously we can use this stochastic oscillation of them to kind of look into how the stars are actually, what they like, how big they are, what they're made of, the age, determining also, for example, from the side of exoplanet science, how old is the solar system that we find. So there's a huge synergy, I think, that is important. For asteroseismology itself, for sun-like stars, I think we are sort of moving past this this barrier where we in the past did a lot of asteroseismology per a bigger scale using the sun as a standard, and now we really do like independent models or even in the model independent observations where we can get like asteroseismic parameters of many stars to a very high precision using the pulsation modes. I think for sun-like stars, as I said, I just mentioned, yeah, we use them for bulk parameters, but we are sort of moving beyond that, I think, for sun-like stars especially, but also more massive stars. And we are looking into, especially the field of magnetism, I think. That's like one of the most difficult things that we know about stars, and exactly how that links to the rotational profile through a sun-like star and massive stars as well. So I think that is going to be what asteroseismology will be moving towards, because we're getting a precision where we really can start to disentangle different effects of the, for example, the Coriolis force or the Lorentz force. And I think these things will be quite interesting to look at with new data, with more precise data. So that was for the solar type stars, but I think that's also more or less true for more massive stars. The massive star community is a bit younger, simply because we didn't have the sun to look at from the very beginning. And also the pulsation modes are very long, so that was difficult to observe from ground. Now with space-based data we can do this, and I think, as I said, we have all these stars that have more massive, they have convective cores, a bit more complicated to understand in the sense that we don't know exactly always what the chemical profile is around the core, how much of this mass is overshooting into the environment. And yeah, that makes it a bit more difficult because they also live much shorter than a normal sun-like star, which live billions and billions of years on the main sequence, and these stars live quite short. So I think that will be interesting to look much more into, like the nitty-gritty details of the physics, I would say. Yeah.
Okay, thank you. I have two small questions on things you showed. So when you showed the mosaic of the field of view with the different cameras, where you showed the Milky Way, and I was a little bit surprised that the Milky Way is not in the central part where you have the maximum overlap. Can you comment on this?
Yeah, crowding. It's simply because of crowding, because we want the catalog of, well, the Plato mission is designed for exoplanets, right? We have to emit that and to do asteroseismology of the targets that we also follow up. So we need enough stars that are sun-like, and that's a compromise between not putting it in the Milky Way. We could do that, but then we completely have the kind of destroy the crowding of it. We have a very high crowding of the targets, meaning that every single target will have a lot of contaminant stars. And we want to avoid that in combination, also selecting enough targets. So it's again a compromise that shows the specific alignment close to the galactic plane, but not like just on top of the galactic plane. It's really to avoid too much stellar noise and just noise in general. So you have made this choice. Yeah.
Maybe it's a little bit connected to the last question of Hans. Then when the instrument is flying and then we have a solid noise model of Plato, do you think it would be possible with your simulation to adapt? I mean how we point and where we put let's say the Milky Way in this case, or is it unrelated?
You mean changing the pointing?
Changing the pointing model, I would say. Strategy.
You could easily do that. It will take you a few months to do the simulations on a supercomputing cluster, and then we could check it, yeah. But I think what you would find is pretty much in line with what I also showed for Mocha. It's like we will have a huge contamination level, and well, even in the core science, we will really be limited by what PSF photometry can magically extract for you. And we also limited about the amount of science that we will get out for the exoplanet community, because we have so much contamination that many of the planets won't even be detected anymore. They're completely diminished by the external flux that's coming into the light curves. So I think it will be not a good idea to do, so I wouldn't recommend it. Also, it won't change. So we have to stick with reality is that this field is going to be observed. We don't have any way out of it anymore, for 2 years at least.
Okay, thank you. On slide 25, where you show the retrieval of modes. So for bright stars, you see that you don't have any real improvement in combining more cameras, right? This is the top right left part of the plot.
Yeah.
Right. So I'm a bit surprised. So do you expect any systematics to be independent between the different cameras? And if yes, which one? And if that's the case, shouldn't we expect some improvement from 6 to 24 in the bright star regime here?
So on your first question, we can use, obviously, yes, we can use the knowledge like from the systematics in different cameras to kind of like know what kind of noise is in there. But you said you're surprised that this is so low, or
no, I'm surprised for the bright stars on the left part.
Here.
Yeah, that the improvement is not that significant, right? And I would expect that in this regime we would be limited by systematics, where we should see larger improvements.
Yeah, I get that. I think the underlying, well, from what I like when I look at this analysis from different types of stars, the underlying reason I think for this is basically what you inject as well. So we here injected a sample of pulsating stars that have certain amplitudes. We modeled this with sort of a log normal distribution, but we know that most of these pulsation modes are quite high. And if you compare that to the noise assumptions that we have in the first place, you can already see that the bulk of them will be observed because they are beyond the 20, 30 parts per million in amplitude. So we know that we can find them just by looking at the underlying noise. And in this regime here, we are like, the stars are so bright that we more or less observe everything and detect everything. Even if you had one camera, you would find almost everything there. But that changes obviously if we would take another distribution of stars that pulsate, then it would look very different, I think. So this is really just because we are hitting the floor of what we inject, I think. It's not so much that there should be a bigger change probably as if you took another distribution.
Okay, another question on PSF photometry. I was really impressed by the details you put in the manuscript on that and how well it performs, right? I was not aware that it was possible to do such good work with PSF photometry. Could you give us some hints on how close to objects, how close you can distinguish two objects, two stars, with PSF photometry, and what would be the magnitude regime of these two objects that you can separate?
I think I already alluded to it a little bit already. I will say the last presentation I saw on this, which was, of course, it's not an algorithm that I have developed, but the last presentation I saw was exactly this threshold where you have like an anchor point saying if the stars are like less than 0.2 pixels, and there is a magnitude difference between the two of around 2.5, then you're in trouble. That's where the algorithm starts to misbehave. And some of the simulation I've done with also two other collaborators, Reza Samadia and also James McCormick, we have seen that the algorithm now on reals, well, not real, but simulated data, is also really having problems in some specific locations with PSF photometry. And what you see is basically a jumping between the two. So the algorithm doesn't know always how to select one star and the other, and so you get very funky phenomena. But that's just one anchor point. I don't know exactly what the other limits are. If let's say if you had a difference of 5 magnitude, could you go much closer? I don't think so. I think the underlying resolution of your pixels also has quite a big effect on this algorithm. But I think I would need to look more into the detail before I could give you a better estimate.
And final question, also maybe staying on this topic of also confusion, which is a big issue. Do you see any important ground-based follow-up to mitigate this confusion problem?
So this confusion problem, I think, I mean, so I was, of course, I like telescopes in Chile, so I think the VLT is always a very nice instrument and probably one of the best ones we have. But I think this confusion itself, if we have high enough spatial resolution to disentangle stars from like interferometry or something where we have multiple telescopes working together, I think that will be definitely the way to go. But we already have a pretty good handle, I would say. Not necessarily all these stars, we need more information, because Gaia is already providing us with quite a lot of this data within 0.2 pixel, and even beyond that we can have stars that are even closer from the Gaia satellite. It's really only if they're super close, then we might need some ground-based follow-up that can give us a better understanding of this, how much flux are falling into a star, into the mask, which will help, of course, disentangle the whole thing. But yeah, I wouldn't, yeah, VLT, that's my best guess.
Okay, thank you.
VLTI, yeah.
How much time do I have? 20, 30 minutes is okay? Good. Very good.
Long chance.
Well, first of all, Nicholas, thank you very much for a very well structured and very accessible presentation that you gave. I appreciate that very much. So you probably know by now that, while it's impossible to stop me from talking the internal defense, I don't really like asking questions to the public defense, unless the student triggers questions, right? And so far, all the students have been challenging me in this respect. It's not an exception today, but luckily for you, Professor Jannsen already asked all of my questions. So I will just... Apparently, I'm one of the most popular people in this room. So I will say two things. First of all, congratulations on this fabulous work. I really, really like it. You mentioned only a fraction of it in your presentation, and you didn't even include it all in your manuscript, the book, I mean. So it's really, really impressive what you managed to achieve in these 4 years. And the second thing I would like to mention is that it's not going to be a huge surprise to people in the room, to the majority at least, that before you started your PhD, Plato SIM tool was already available thanks to the efforts of your supervisors. But I would like to thank you a lot for making this tool accessible with the help via the Platonium tool. I also appreciate that very much, and I think it's a huge contribution to the Plato consortium in general. So congratulations, and thank you very much.
Thank you so much, Andrew.
No questions from my side.
One question only. A follow-up on one of Hans's. So about the intrapixel variations. Suppose we would take it into account. Do you have any idea how it would affect your MOCA simulations?
Luckily, so that's the nice thing about sort of why we chose to go in a little bit also this direction. When we wrote the paper on Plato Sim, it was already a little bit apparent that this regime is not the best to go in. So that's also why we chose to go a little more fainter. But actually, it doesn't have a big effect. If you took this diagram of the precision, the signal's noise over magnitude, we are really not working in a bright regime. And the bright regime, you can have up to maybe 10 to 20 parts per million added noise, let's say. But when we are in the photon noise above, let's say, 10 magnitudes, which we typically have been in our simulations, we don't see that at all. So we are completely dominated by photon noise, or as in this case here, if we include more instrumental systematics. Yeah, but it was dedicatedly tried to avoid it, that regime, for that reason exactly. Yeah.
Okay, to close, so I will double down on all the congratulations that you got so far. And I have tiny questions to close, also triggered by your presentation. You insisted a lot on supermassive black holes, and that's what you want to work on. In the future, you give a lot of details on the catalog of USOs that you have. My question would be more if you want to write a proposal on that. You also mentioned LSST, so how will you convince the panel that you need Plato? That what you want to propose, whereas, because you showed the parameter space covered by Plato, the planets, so in which sense is Plato unique for the supremacy of black holes compared to other survey facilities?
Did you mean compared to other surveys, basically?
Yeah, SST or what is
Yeah,
future telescopes with ESO and so on.
I think so. In the case of if you take like another survey that is going to be probably one of the biggest one for extragalactic physics, like the LSST, that is located in the southern hemisphere. So we have the benefit of actually going to the north if we do so, and observe spiky. But also there will be a high precision catalog available than if you would go for that. I would say that's already a huge perk to it, that you would actually have a quite good place in the sky where no other bigger survey for ground-based extragalactic surveys are looking. So I think that will be an added benefit. But I do agree, like this is one of my own concerns, obviously, with this project, that there needs to be more added value, and I still need to find more added value if Plato will be able to be like hunting down these things, because right now, obviously, we are playing really with the faint limits, and so we need to test it more before I can give any conclusive remarks, I'll say. Sorry.
Okay, then I look to the audience. Are there any questions from the audience? There have been already a lot of questions, but maybe there's some things that still need to be solved or answered.
First, second.
Last chance? No? If no, then the jury will retract for deliberation. Honored.
Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee appointed for granting the doctoral degree in science, astronomy and astrophysics. Nicholas M. Jannsen has presented to the faculty the PhD thesis on the topic mock simulations for ESA Plato's mission, exploration of supermassive stellar objects with the next space-based photometric legacy, in partial fulfillment of the requirements of the PhD in science, astronomy and astrophysics. And Nicholas M. Jannsen has defended this thesis in public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Nicholas M. Jannsen the degree of Doctor in Science, Astronomy and Astrophysics. By obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as prescribed in the ALEA European Code of Conduct, reliability, honesty, respect and accountability. I close the session. This is for you. This is the preliminary. You get a final one later. And then for the seat, you have to sign this one. I don't know if you have a pencil. And that goes back to the faculty then. Yeah.
Thank you so much.
Thank you. So the official session is closed, but I think the promoters want to say a word.
Okay, technology is not my thing. Dr. Nicholas, I have the privilege to congratulate you like that. But of course, your real promoters are standing next to me, as you will agree. Joris and Pierre did all the daily work. Nevertheless, I was still very glad to coach you on more general aspects of a PhD and to follow your PhD path in your simulation work and mainly, of course, on the non-radial pulsators that you discussed today. When you started off, actually, we did not spoil you as we do with most of our PhD students, in the sense that we gave you some very vague topic, you know, in your first year. Help the Plato simulator and make some sensible simulations. That was your task we sort of gave you. And on top of that, you had to comply with 3 supervisors. And I can tell the audience, for those who are unaware, that we are quite different people with different demands and different styles. And yet you managed. The first year was a bit hard, I think, right? But here we are today. It shows that you actually managed very well. Well, you meandered in our institute in the beginning, but also in the city of Leuven. And actually, I want to stress that Nicholas is great in some aspects, and that's not only science, but he also came and told me when I had to organize stuff where all the good bars and restaurants were in town. He knew that way better than me, and that's actually very helpful even during COVID times when things were a bit hard, I really appreciated that and was happy to see that. And I really want to mention that today. It's not only about work. So you grew also in your role. Magali already stressed that earlier today, to help the Plato community, a big diverse community again, with the use of Plato Sim and the user-friendliness. And so I want to stress that you're actually, I think, well, one of the very first students that I supervised who provided such service in a really competent way, caring about a user in a very patient way. And I cannot stress enough how important this is. So I call that your excellent skill in emotional intelligence, along with your technical skills. And you should never underestimate that, how important that is actually, whatever you will do next. So please keep on exploiting these two types of intelligences, nicely intertwined. We will have the pleasure of having you a while with us still here in Leuven. Huh? That's of course nice for us. And then you will likely move on to some other adventures, whatever they are, wherever they will bring you. I am absolutely sure that you will act as a good ambassador of our institute. And that's also a very important skill. Now, as you know, I tend to make silly promises. And as you also know, I already had a Danish student where I have completely proven my incompetence. So, som det här var kan zielen mais usfar, mitt danska in katastrofe. Så, jag vill göra det kort. Hjärtligt tilllycka med din doktorgrad.
Yeah, so Nicola, congratulations. It's been expressed by all members of the jury in different ways, and everything which was said is totally true and more. So congratulations for the scientists that you have become and demonstrated today to be. Connie mentioned 3 supervisors and how easy it was to handle all of those. So I would like to thank the supervisors. Don't believe Connie, it was very easy. Thank you, thank you. It was a smooth collaboration, as always. It was a pleasure. So I would like to mention a 4th person, which you will agree, I think, upon as being very important in this thesis. He will not put himself forward, but as in many other aspects of the Institute, it's someone important. I want to thank also Andrew for his participation and for support he provided in this thesis. So thanks a lot. And then I want to thank you, Nicola, for everything you have done, for taking this project from a already extremely well-defined project into something extremely well-defined, to establish collaborations throughout the consortium, which are really fruitful collaborations in the sense that they bring much more than some of the expertises of the people around the table. And so Magali also expressed how fruitful this was for the mission as a whole. So that's very important, and I want to thank you for that and congratulate you for that. And also congratulate you for the fact that your thesis, on the one hand, contains much, much more work than what you have gathered in this book or in this presentation. And you've been also important in the Institute for many other aspects. So that's one aspect. And also for the fact that it's encompassing all aspects of the mission as well technically. So you are the real bridge between all of the technical aspects which need to be very well understood to make it into the simulator and to be properly taken into account at that level. And all the science to also have the proper signal injected and the proper interpretation of it. So that's really remarkable. So congratulations for that as well. And then finally, for simply who you are, a very multifaceted man, a man of conviction, skier, scientist, fantastic colleague. And so thanks a lot. Tilleke Otak.
Dear Dr. Jannsen, dear Nick, congratulations, you earned your doctoral degree. And before you stands a very proud supervisor, I can say a very proud team of supervisors. You belong to the generation of students that had to do part of their PhD during COVID. And so we all know that it's not easy, but not only did you make it work, I believe you emerged actually stronger. That's already an achievement on its own. If there's one thing that is most rewarding for a supervisor is to see your students grow as a scientist in the PhD. And for many students, it goes with ups and downs. That's very normal. But in your case, I saw a steady growth year after year. The Plato community is very international, and you took full advantage of that. I introduced you at the start of your PhD, but you quickly acted independently and carried out the collaborations with colleagues from the UK, from France, from Germany. And when I ask them, I get nothing but positive feedback from your work with them and about the very nice software package that you wrote. You really set the standard here, not only for the current team, but also for the PhD students coming after you. Now, one similar comment, being guided by people like Pierre, Andrew, and I, it's not always easy. If during a meeting we were all drawing at you in the same direction, we would call it a successful meeting. The upside is that you quickly learn to be vocal about what you think is the best, and I'm sure this will benefit you in the rest of your life. So Nick, you will not only be remembered as an excellent scientist, but also as a super social guy, as a guy who loves observing and feels most at home inside an observatory, and finally also as the guy who has talent in guiding students, actually. We are very happy that you agreed to stay a little longer at IVS. For the next steps, Pierre, Connie, and I would like you to remember the sky is the limits. And to emphasize this, we brought you the following gift, and we leave it up to you to find out, but at least enjoy.
All right, let me turn on this one. Although you can probably already hear me, don't speak too low anyway. Thank you so much for all these kind words. I don't want to drag it too far because we're already a bit over time for reception, which is equally important. But I want to really highlight, as you said, it's been some 4 years with different supervision. And I'm so happy to have all of you as my supervisors, very diverse supervision. I'm super happy about that. It taught me a lot about actually being in science, and also from not only the scientific point, but also political. So I think that's extremely valuable. I also want to thank someone that's not here, actually, Dries, that's a software guy that's been helping me a lot during COVID, actually, also mental support, and also from the software side, he's one of the main developers on PhD. And without him, I wouldn't have learned as much and as fast as I did, and I think that's really, I should give some credit for that. And to, Connie, Mamsi, you're always there for us, so you already know that, and I love working in our little group, so that's also why I stay. So I think that's already a big kudos to you. And for you, my main supervisors, day to day. Pierre, I think I only have a little anecdote of good times wrestling with you in a bar in somewhere, I don't know, another country at a Plato meeting, and I won. So, but I really love that we can both have fun talks and scientific discussions, and you are definitely one of the people that keep me on leash when I have some crazy ideas, and yeah, you have been great support all the way through. And the same to you, Joris. I think we had so many good discussions over Play the Sim and what should be involved, and I really love to be in this community of doing simulations. Obviously, I'm an observer by heart, but but I think this is a good interface to learn something about future missions. And yeah, it was one of the most, like the nicest experience I had so far. It was actually not that long ago when we were in Göttingen. I'm not the best person to always reach out for help when I'm sick. So you came by with a bag of drugs and helped me a lot. So thanks for being my local drug dealer. That's great. And I also want to just thank you, Andrew, a little bit, because although that you're not officially a supervisor, you have definitely had the role as that. And I think 2 years into my PhD, we really found out what I was doing and which way we should go, and that's also one of the reasons why I'm here today. So thank you so much for that. And for that, actually, I have a little gift for all 4 of you, because I think you all helped me so much. I also have one for Dries, but he couldn't make it today. He has small kids, so this one is for you, Connie. And I think this one is for Andrew. And the 2 other ones, here we go. Your name should be in it, so you can probably find it. But this is for better times. As Connie said, I like to go to bars, so of course there's some alcohol involved here. So anyway, I just want to close it here and say, like, we have a reception waiting. I think we should go in and have some fun. Yeah, thank you.